The limitations of current hate speech benchmarks are exposed by their inability to capture linguistic and topical diversity, relying heavily on hate lexicons and libelous identifiers. To address this, the authors introduce GotHate, a large-scale code mixed crowdsourced dataset of approximately 51,000 Twitter posts that encompasses diverse languages and topics, better representing real-world variability in hate speech. This neutrally seeded dataset comprises examples of hateful, offensive, provocative, and non-hateful tweets, allowing for more comprehensive analysis. Compared to existing hate speech datasets, GotHate showcases novelty and complexity, highlighting the challenges of classification in a text-only setup. The authors benchmark GotHate with 10 recent baselines, demonstrating its difficulty. To enhance detection, the authors propose incorporating endogenous signals, such as user timeline information and ego network. They develop HenEmbert, a modular, multilingual, mixture of experts model that enriches the linguistic subspace with latent endogenous signals from history, topology, and exemplars. This model outperforms the best baseline by 2.5% in overall macro F1 and 5% in hate class F1, emphasizing the importance of contextual and endogenous signals in improving detection accuracy. In collaboration with Wipro AI, the authors are developing a semi-automated pipeline to detect hateful content, aiming to tackle online harm. This work addresses the limitations of current benchmarks, providing a more comprehensive approach to understanding and mitigating hate speech on social media. Existing hate speech datasets are limited by biased annotations, inadequate coverage of nuanced hate speech constructs, and a lack of diversity in topics and languages. To address these limitations, the authors propose geopolitical topical hate, GotHate, a comprehensive fine-grained hate speech classification dataset. GotHate covers 7 topics, 3 geographies, and 3 languages, mimicking real-world online hate speech discourse with a neutral seeding policy and fine-grained hate labels. The authors illustrate the complexity of GotHate with representative samples, highlighting the challenges of hate speech classification. They also propose a novel model, History Exemplar Network Infused MBERT, HenEmbert, which incorporates endogenous signals such as users' historical data, social connections, and posting history to improve hate speech detection. The authors' main contributions include the release of GotHate, a cross-dataset study, the incorporation of endogenous signals, benchmarking with 10 baseline methods, and the development of a content moderation pipeline. They ensure reproducibility by making their source code and sample dataset publicly available. The authors hypothesize that real-world online hate speech rhetoric around a given topic exhibits few semantic and linguistic differences. They also propose that incorporating endogenous signals can improve hate speech detection and highlight the importance of considering contextual information, such as who is posting what, in content moderation. GotHate and HenEmbert are designed to improve hate speech detection by incorporating endogenous signals and considering the complexities of real-world online hate speech discourse. The author's approach has the potential to enhance content moderation pipelines and mitigate the spread of hate speech online. This study revisits hate speech benchmarks by replicating metadata-rich dashboards for content moderators, focusing on hateful content on Twitter. Leveraging the Twitter API, the researchers compiled a corpus of 51,367 tweets, dubbed GotHate, which spans 7 socio-political events across the USA, UK, and India. The dataset categorizes tweets into 4 labels: hate, offensive, provocative, and neutral. Critically, the paper highlights the importance of understanding hate speech by defining labels based on vulnerability groups, introducing an order of priority for labels. The data annotation process involves a 2-phase continuous validation approach, ensuring the accuracy and reliability of the labels. The study underscores the limitations of automated speech detection systems, emphasizing the need for human involvement in accurately detecting and categorizing hate speech. By doing so, it fills a significant gap in current hate speech detection methodologies, which often rely solely on automated systems. The GotHate dataset provides a valuable resource for content moderators, policymakers, and researchers, enabling them to better understand the nuances of hate speech and develop more effective strategies for mitigation. The authors introduce GotHate, a novel hate speech dataset annotated using a rigorous trois-phased continuous validation process. Annotation guidelines are refined until achieving a Krippendorff's alpha of 0.8, ensuring high interannotator agreement. The dataset is then crowdsourced to a professional annotation company, where 10 annotators attain an average agreement of 0.71. Notably, 60% of disagreements occur in the provocative class, highlighting the challenges of annotating hate speech. Got Hate is compared to existing benchmark datasets, including Davidson, Founta, HASOC 19, OLID, Hataval, and IMP Hate. To quantify interclass similarity, Jensen-Shannon divergence is employed, revealing that lower divergence values correspond to increased difficulty in classifying and distinguishing between classes. Results show that Got Hate exhibits lower divergence values for specific class pairs, such as hate provocative and neutral provocative, indicating these classes are harder to separate. Furthermore, the authors analyze interclass similarity across various hate speech datasets, finding that Got Hate has a lower divergence between hate and neutral classes compared to other datasets. This suggests that Got Hate is a challenging dataset to classify due to its topical similarity and use of neutral seeding during data collection. The authors hypothesize that Gothat's low interclass divergence will make it difficult to classify, and provide extended experiments in the appendix to support this claim. Revisiting hate speech benchmarks, a comprehensive analysis of dataset performance and generalizability. The paper presents a thorough examination of hate speech datasets, including Got Hate, Founta, Davidson, HASOC 19, OLID, Hataval, IMP Hate, and Retina, to assess their performance and generalizability. A modified NGRAMTFIDFBASED logistic regression model is employed to compare performance and evaluate adversarial validation. The results reveal significant variations in performance among datasets, with Got Hate exhibiting the lowest macro F1 and Matthews correlation coefficient scores. Adversarial validation reveals that Got Hate shares similarities with HASOC 19 and Retina in terms of feature space. Cross-dataset performance comparisons demonstrate that Got Hate generalizes better than HASOC 19 and Retina when tested on each other's datasets. This suggests that Gothat's lower performance is not due to a lack of generalizability, but rather a result of inherent differences in the dataset. To address these limitations, the authors propose a novel modular mixture of expert setup, Henembert, designed to enrich textual representations and improve hateful content detection. This approach has the potential to enhance the accuracy and robustness of hate speech detection models, ultimately contributing to a safer online environment. The authors present the model architecture of Henembert, consisting of 4 modules: base language, exemplar, timeline, and graph. The base language module employs multilingual BERT to generate embeddings for the exemplar and timeline modules. The exemplar module utilizes dense retrieval via SBERT to augment the signal from within the dataset, retrieving top exemplars based on cosine similarity. These exemplars are concatenated and transformed to extract salient features, which interact with the language vector via multi-headed cross-modal attention to generate an exemplar-infused language representation. The timeline module leverages users' historical data to provide crucial insights into their propensity for posting hateful content. Historical posts are concatenated and undergo 2 layers of LSTM to generate a temporally enriched vector. This vector is then transformed and interacts with the language vector via multi-headed cross-modal attention to generate a final feature vector. The graph module examines users' ego networks and extracts their interaction patterns. A directed homogeneous network is constructed, and edge weights are added to distinguish different interactions. The module receives input from the corresponding user's ego network and enhances the input embedding via cross-modal attention. Ultimately, the reasoning module concatenates the 3 endogenous signals to obtain a contextric embedding, which passes through an attentive feed-forward block for classification. Equations 1, 2, and 3 describe the self-attention mechanism and cross-modal attention in the exemplar module, while equation 4 depicts the final feature vector generation in the timeline module. The authors highlight the significance of considering users' historical data and ego networks in detecting hateful content. Formulating the ego network involves representing individual nodes as vectors, capturing their local network structure and attributes. This is achieved through a novel network-aware language representation generation process, which considers both node centrality and community affiliation. The reasoning module is a critical component, as it integrates information from each module via mutual interaction, enabling the model to capture complex relationships between nodes. This coalescence of information facilitates a deeper understanding of the network's underlying structure. Performance comparisons between Henembert and its variants, as well as baseline methods, reveal significant advancements in node classification tasks. Error analysis highlights the benefits of incorporating network-aware representations, with notable improvements in class-wise precision and recall. A detailed breakdown of these results demonstrates the model's ability to accurately classify nodes, even in the presence of class imbalance and noisy data. The infusion of endogenous signals further enhances performance, with each latent signal contributing independently to improved node classification accuracy. These findings underscore the importance of incorporating network structure and latent signals in language representation models. Henembert, a variant of the multilingual BERT (MBERT) architecture, demonstrates improved performance in detecting hate speech. Notably, combining all three signal variants yields enhanced F1 scores for hate and provocative classes. The graph module exhibits the highest performance for the offensive class, indicating distinct interaction patterns. Error analysis reveals that while both models excel in identifying explicit offenses, Henembert's contextual understanding proves beneficial for tweets requiring post-contextual knowledge. This contextual understanding enables Henembert to better distinguish between hateful and non-hateful content. Moreover, the development of a content moderation pipeline is underway, integrating Henembert for real-time hate speech detection. This pipeline has the potential to significantly enhance the efficiency and effectiveness of online content moderation. It is worth noting that the current state of hate speech datasets has been explored in related work, highlighting the need for continued research and development in this area. As online hate speech continues to evolve, the importance of accurate and efficient detection methods cannot be overstated. Henembert's improved performance and contextual understanding make it a promising tool in the fight against online hate speech. Hate speech detection systems have long struggled with data curation and deployment. To address this, the authors introduce the Geopolitical Topical Hate Dataset, or GOT-HATE, a novel benchmark that spans multiple languages and topics while minimizing slur terms. This challenging dataset is designed to test the limits of hate speech classification, with benchmarked results against various methodologies. A key innovation is the integration of History Exemplar Network-infused MBERT, or Henembert, which enables contextually rich hate speech detection. This approach involves querying a user's timeline and interaction history to extract their most recent online footprint, which is then combined with an existing exemplar base to inform detection. By leveraging this context, the system can semi-automate the flagging of hateful content, providing signals and predicted labels to content moderators for review and confirmation. The GOT-HATE dataset and Henembert methodology offer a robust framework for hate speech detection, tackling the complexities of real-world online discourse. By incorporating user history and interaction data, this system can better capture the nuances of hate speech, providing more accurate and reliable detection. Ultimately, this approach has significant implications for the development of more effective content moderation tools, enabling a safer and more inclusive online environment. Hate speech detection on social media platforms is a pressing concern that requires a nuanced and context-sensitive approach, particularly in a multilingual context. Explicit and implicit forms of hate speech necessitate the development of sophisticated methodologies. Deep learning techniques, such as BERT, Node2Vec, and graph convolutional networks, have been employed to tackle this problem. However, the dynamic nature of language and concept drift phenomenon, where hateful content characteristics evolve over time, pose significant challenges. To address these challenges, a proactive approach is proposed, involving the normalization of hateful content to reduce its intensity before it spreads online. The reliability of hate speech detection models is crucial, and metrics like Krippendorff's alpha, which measures interannotator agreement, are essential for evaluating model accuracy. Furthermore, ethical considerations, such as the risk of amplifying hateful content during data collection, must be addressed. A collaborative effort between researchers, policymakers, and social media platforms is necessary to develop and implement effective strategies for mitigating hate speech online. Continued research is needed, focusing on developing more sophisticated models that capture subtle forms of hate speech and adapt to changing linguistic patterns. The ethical implications of this research and its potential impact on society must also be addressed. The paper revisits hate speech benchmarks, focusing on data curation and system deployment. It discusses various aspects, including hate speech diffusion on Twitter, the spread of hate speech in online social media, and the detection of hate speech using machine learning techniques. The authors highlight the importance of understanding hate speech in different contexts and the need for robust detection systems. They also emphasize the role of transfer learning in improving hate speech detection models. The paper concludes by discussing the limitations of current approaches and the need for further research in this area. The limitations and challenges of collecting and annotating large-scale datasets for hate speech classification are acknowledged, including the subjective nature of hate and the lack of standard definitions. The authors highlight the limitations of their dataset, Got Hate, which suffers from annotation biases and disagreements. To improve hate detection, a more neurosymbolic approach is suggested, integrating common-sense knowledge, factual analysis, and stereotyping motives. Ethical considerations are emphasized, recognizing that datasets and language models can be used for both good and bad. Early flagging and moderation of hate speech are stressed to prevent harm to vulnerable groups and promote a holistic view of hate speech. A comprehensive overview of benchmark hate speech datasets is presented, including Got Hate, Founta, Davidson, HASOC 19, OLED, Hataval, Imp Hate, and Retina. These datasets vary in terms of labels, size, and hate percentage, with shared task-based datasets having a more equitable distribution of hate labels. Extended experiments employ MBERT to capture interclass similarity via maximum mean discrepancy, MMD, and perform within dataset and cross-dataset validation. Results show similar patterns across experiments, highlighting the challenges of hate speech classification. Annotator details are provided, including demographics and political views, chosen to ensure diversity and minimize bias in the annotation process. This section underscores the importance of acknowledging limitations, ethical considerations, and the need for more nuanced approaches to hate speech research, while providing a comprehensive overview of benchmark datasets and extended experiments. The Got Hate dataset is curated to focus on socio-political topics, featuring tweets in diverse languages including Hindi and English, annotated by native speakers. A cross-dataset performance comparison among Got Hate, Retina, and HASOC 19 shows the MBERT model outperforms others in both within dataset and cross-dataset training and testing scenarios. Sample annotations illustrate the dataset's complexity, emphasizing the need for contextual understanding for accurate classification. The authors highlight the importance of high-quality exemplars for effective training and validation of models. Statistical models and deep learning models are used, achieving a macro F1 score above 70% on the validation set. This analysis presents a comprehensive overview of the Got Hate dataset, its annotation process, and model performance, emphasizing the significance of contextual understanding and high-quality exemplars for hate speech detection. The performance analysis of competing models in hate speech detection emphasizes the importance of contextual information. Accuracy as a metric is limited in hate speech datasets, highlighting the significance of the F1 score for a balanced precision and recall. Various models are evaluated, including NB, LR, SVC, Davidson, CNN, LSTM, Founta, MBERT, ARHNet, HERT-BERT, and HENEMBERT. Contextual embedding-based systems like HENEMBERT provide a more balanced precision and recall, leading to higher F1 scores. The consideration of user timelines and network-level signals is also crucial for better detection. In evaluating hate speech benchmarks, A comparative performance analysis is conducted between the proposed model and a logistic regression (LR) model, referred to as M2. The analysis leverages a dataset consisting of 354 annotated, 293 predicted, and 158 overlapping users. The proposed model exhibits a more balanced precision recall per class, ensuring equitable treatment of all groups and classes. Notably, it yields higher false positives for hate classification compared to the LR model, with a performance of 44.6% and 13.5%, respectively. This aggressive prediction of hatefulness is advantageous in real-world scenarios, as it enables moderators to flag false positives in the final reporting, thereby protecting targeted groups from a higher volume of hateful content. This performance disparity is critical, as it highlights the proposed model's ability to prioritize the detection of hateful content, even if it means flagging some non-hateful content for review. This approach is particularly valuable in online platforms, where the timely removal of hateful content is crucial for maintaining a safe and inclusive environment.